say what this is. The great Professor Bill Hunter, who is going to talk about variability from his perspective. Is that correct?
Yeah. Okay. Yes. Okay. Well, I believe that a good way to start teaching statistics, a statistics course, if somebody wants to focus on variability right away, is to, let me describe it in words and then I'll show you some formulas. But it would go something like this: that this is a better way, I think, than the way we do it. Not the best way, but a better way. That there's a response Y that we're measuring. And it could be anything we're concerned about, but the yield of a chemical reaction or the temperature of some room, some laboratory at different times of the day or whatever. And that's the response. And the point is, if you were teaching a group of students, that they would actually, from the very beginning, measure the yield of the chemical reaction, or measure the yield of the chemical reaction in a reactor back where they work. They collect some data and bring it to the first lecture. Or they actually measure something during the lecture, the temperature in the room, or whatever it is. And then to look at the data and say, well, these numbers don't all come out to be the same. Now, it can be that the data are collected under what are called, quote, identical conditions, unquote, where everything is supposed to be held steady. And you might expect that the response values would stay steady too, but if you measure them carefully enough, and if it's the usual situation, then you're not going to get the same same answer every time you measure the response, whatever it is. Well, why don't you get the same answer each time? Well, the way the statisticians usually do this, they say that there is some true value that you should get, and then there's something added onto it, namely experimental error. And experimental error is something that, I don't know, somebody sitting on a cloud somewhere sort of sprinkles down on your true value that you were going to get, that messes it up so that when you get to look at it, you don't get what you should get, but you get the true result contaminated with this experimental error, which is random. I mean, it's just sprinkled down and some value, plus or minus something, hits your true value, and then that's why you don't get the same answer. Well, I think a better view is that the reason you don't get the same answer 2 times in a row, where all these numbers are different, is there's a reason, or there's more than one reason why you don't get the same answer, and that is some critical variable. Well, first of all, you got to recognize that the response value that you do get as a measurement is influenced by millions of x's. Well, let me call them x's. Let's say the response is y. And then the variables that affect that y, we label those x's. So then we call them x1, x2, x3, x4, and so on. And there may be some of those x's that are very important, although we don't know they're very important, like x109, 109th x. And the main reason why we don't get the same answer the second time is that x109, unbeknownst to us, has changed its level between the first time we make a reading and the second time we make a reading. And of course, there may be more than one of these other variables, lurking variables, if you want to call them that. That's a name that's been coined by George Box to describe these variables that are lurking back there in the background and affect your response, although you haven't figured that out yet. Well, then the problem usually is when you have these observations y, and they're not all the same, is to somehow deal with that situation. And what a lot of science and engineering, a lot of what that's concerned with in a sort of research environment, say people working on PhD dissertations and producing a thesis, what many dissertations in science and engineering have to do with is how to get a mathematical model that would describe the response of interest in terms of some x's that are the really important x's, the really important variables. And it may be only two variables, like let's say x1 and x2. And then you build a model that says the response y depends on x1 and x2. Primarily in that particular model, this function of x1 and x2 is the contribution of that PhD candidate to the literature and to the field, is they have a model now that will describe a lot of what goes on with the system simply in terms of two x's, and that's a great advance. Well, what to do with all these other x's? Well, it depends. I mean, if you're interested in developing even a more refined model, you can think of dragging in x3 and x4 and so on, other x's. Or discover that x109 is a very important variable and you want to put that into the model. Or you discover that x109 is very important, but you don't want to drag that into the model because it has to do with the relative humidity in the laboratory, and nobody really cares about the relative humidity in your laboratory or their laboratory. You just want to realize that relative humidity is the key factor, and you want to control it. So when you do this kind of experiment in the future, you do it at a certain relative humidity, and then your model will work at different levels of relative humidity, and your model works as long as you control the relative humidity. But of course, sometimes that'll be unsatisfactory if a company has relative humidity as a product that's influenced by relative humidity and is selling the product, let's say nationwide in the US. They've got to be concerned about how the product responds to, how its performance responds to the relative humidity. Because if they're going to sell a product in Mississippi, and if they're going to sell it in Arizona and North Dakota, they have to have a robust product that will work in all these different conditions. And so, therefore, they've got to be more serious. It's not good enough for them to have a model that works, sometimes in one relative humidity and sometimes in another and sometimes in another. They've got to probe deeper and learn how the relative humidity actually affects things and build that into the whole system in a different kind of way than would be acceptable, say, in a PhD thesis. They have to go further. And so they have to try to elucidate, they have to try to dig out the effect of these other x's. Okay, now let me just review what I've just said in terms of some equations, and they're over here. The first equation is the first thing I said, which was the response y is some function of, well, millions of x's. I mean, really, literally millions of x's. And we don't know that capital F. But there is a function. I mean, there is cause and effect. At least that's what I believe. And these different x's influence y in different ways. And not just singly either. They interact with one another and so on. Now, the job of any scientist is to try to create a mathematical model in terms of a subset of these, let's say x1 and x2. And let's say that does pretty well, whatever that means, at describing the observed values of y. But we do have, but then it never fits perfectly, and that's what this is. And that's what's left over. That's the lack of fit, or that's the extent to which this model doesn't match up with the y's. And this is a function of all the x's again, including, by the way, x1 and x2. Because this model may be linear in x1 and x2, but the true relationship between x1 and x2 and y may not be linear, but may be nonlinear. So the nonlinearity part, if you will, is still left over in this piece. But then there are all these other x's that have just been ignored entirely over here. And if you can get to know something about some of these x's, like x109, the relative humidity in the laboratory, is very important, then you can use various devices, depending on what your purposes are, like blocking on different locations, if you wanted to do that, with this being relative humidity. So you can use that kind of device. You can use randomization in the hope that you can, in a sense, neutralize these by scrambling them up with randomization. But randomization and blocking aren't perfect answers because, of course, if your answer depends on ambient temperature, and that's x109, say, and you've done all your experiments in the summertime in Madison, and then someone in Alaska just tries to repeat them in colder temperatures or in the winter in Alaska, then this is going to be completely different from what it was in, this is ambient temperature again, that x109 will be at a completely different level in the Alaska experiments than they were in the Madison experiments, even though you randomized in Madison in doing the experiments, because you can randomize all you want and you'll just have summer ambient temperatures here. And no matter how much you randomize, you're not going to get in the winter temperatures because I just said we're going to do the experiments in the summertime. So randomization isn't perfect, blocking isn't perfect, but there are techniques such as that do help to some extent with this part over here. Now what statisticians do, they tend to start their papers and lectures and everything else down here at step number 3 and just say the response is some model which they most of the time assume is just true, period. That's the true value, which is a huge assumption. But anyway, they assume it's true, and then there is something left over which they call the experimental error, which they endow with all kinds of wonderful, or I should say I'm a statistician, and we endow with all kinds of wonderful mathematical properties that makes the mathematics work out very nicely from then on. And there is some justification for some of these assumptions that are made over here, like normal error and so on, because errors, when you look at them in practice, they do tend to be normal. However, they don't tend to be independent, which is a key assumption that's often made. And there are other assumptions that are made over here. And it may not be normal, it may be Poisson or binomial, or lots of different distributions can be assumed over here. But that's the big word, is to assume that this model is right and assume that this has some nice statistical properties, and then the mathematics goes through very nicely. Now this can be complicated if you want to make it even more complicated, and in many situations more realistic. There may not be one y like the yield of the chemical reaction, but there may be performance characteristics of this product that are also over here, like y2 might be how shiny the product is, or how well it tastes to customers. Or it can be quantitative things, it can be qualitative things. So you may have not just a single number over here, you may have a set of numbers that's a function of all these things. And then furthermore, you get into questions in many situations where you don't know, I mean, these are supposed to be x's you fix, like temperature and pressure, and you run your experiment, something like that. And then you get out something like a yield or a taste or a performance or something. But in many situations, you don't know which you just given taste and temperature and pH and how the customers like it and various aspects and so on, and temperature and pressure and concentration and lots of measurements you might have. And you don't know which are x's and which are y's, because the way I've done it, I've said that the x's are what are sometimes called the independent variables, and this is the dependent variable, and these cause this. But a lot of times you can't tell just looking at a situation, which are the x's and which are the y's? So then it gets even more complicated. And maybe a better way to begin is just to say that 0 is equal to some capital G, and then it's a function of x1, x2, x3, and so on, and it goes to x109, and it also includes, I mean, this string here of x's actually includes these y's, so everything is just a measurement, and we'll call them all x's or all y's, it doesn't matter. So this string here contains everything that's here plus everything that's over there, and then you could rearrange this so it's equal to 0, and so that would be perfectly general and well, not as helpful, I think, to beginning students as this way would be, because I think they can identify the first one. So that's why you get variability, because of things like x109 and then the next one and the next one. You've got to collect information. If you really want to understand the system, then you keep studying and studying and studying, and moving some of the x's in the g function, this one, over to the f function, and that's when you learn. And that's how you reduce variability, because this is where the variability is coming from, because some of these jump around, and when they jump around, then that's one source of the variability in the response y. I think students would take to this better than starting off with this model plus a random error that has all these wonderful properties, which is where we tend to start right here. It would be better to start here and let them in on the truth, or at least a lot of the truth. So that's my short blast on variability. It's that.
You say that this is a fairly unique approach to variability?
Well, it's just not the way we do it in classes. And I'm just proposing putting in the first couple of steps and saying that's what the task is, that we have some numbers. And I think it's most helpful for beginning students to get into this, to think of y's as responses and x's as being the variables like temperature and pressure that you could set in an experiment, and y being the yield or something like that.
Mm-hmm.
And that's the problem. We're trying to elucidate that kind of relationship. And if we can write it down in a nice simple formula like the yield is equal to some nice linear function of x1 and x2, that's a huge advance. And then in physics and chemistry and a lot of the physical sciences, enormous strides were made in developing models of that kind. And if you could express it mathematically in that kind of way, then that was a big advance. And then the people in social science thought, okay, we'll do the same thing over in social sciences, but well, it hadn't worked out so well in social science, because you're not, well, there's all problem which is x and which is y. When you reduce the prime rate, then what's going to happen with the trade deficit and all that kind of thing. It's just devilishly hard to sort out in the first place which are the x's and which are the y's, because some of the things you change, some of the x's you change and hope to see a result in y, it doesn't work so neatly, because the y will influence something else, which will come back and influence what you changed in the first place, the prime rate or whatever. So it gets all tangled up that way. But another thing is they can't design experiments very well. They can't say, although some attempts have been made, especially recently, to change some basic x's about how much money people are given in kind of programs to help people who are below the poverty line, and will it make them work more or work less, and what will happen? They have the big controlled experiment, and they go about doing things. but they have to have tremendous organization in those experiments to randomize the X's and so on. Sometimes they just end up with trivial kind of answers in the social sciences, which say things like, well, if you have more money, you spend more money, or things like that. One of my social science friends said the definition of social science is hacking one's way through an open door. And, well, it's kind of like that's the conclusion you come up with a lot of times, because they can't run controlled experiments, so they can't, in a more or less unambiguous way, figure out what the relationship is between the X's as factors that you manipulate and as causes for what happens to the Y's. So that's a whole interesting kind of area.
What kind of area do you want to explore next in this conversation? Do you want to talk about your spring course?
Yeah, that would be fun.
Okay.